Welcome to video 2.1 in our first Principles of Astrophotography series covering angular distances.
We sometimes get half arc-second guiding with our equipment, but how big is an arc-second really? And is half arc-second guiding good enough to resolve stellar disks?
Short answer, no. Great questions. In this video, we define angular distance and we define 4 units that are used to measure it, including the arc-second.
We also introduce scale models for these units and show that half arc-second guiding is not nearly good enough to resolve stellar disks, except for the sun, of course.
Told you. This video is based on section 2.1 of our First Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards. Let's talk sensor sensibility.
All right, angular distance. The angular distance between two celestial objects is the angle between the line from the observer to the first object and the line from the observer to the second object.
So here's the observer. Here's one object. Here's the second object. This is the line from the observer to the first object, the line from the observer to the second object, and the angle, this angular distance, is this angle between these two lines. So it just means that if you're looking at something, one object there, one object there, the angle between those two lines of sight is what the angular distance is.
And for our purposes, that doesn't necessarily have to be objects. It can be points on an object, or it can
Yes,
be
it can.
points in the sky that aren't an object.
That's right. So that from your perspective, looking at this button and that button, there's an angle between those two, and it's an angular distance. It doesn't measure the distance in meters or centimeters. It just measures the angle between them. And normally, we don't really worry so much in astrophotography about what the distances are, the actual distances are. Sometimes it's interesting to know, but angular distances are really, really important. They're denoted by the Greek letter theta. So this Greek letter is basically an O with a line through it.
Angle units. There are 360 degrees and 2 pi radians in a circle, 60 arc minutes in a degree, and 60 arc seconds in an arc minute.
So that's a mouthful. Everybody's heard about the fact that there are 360 degrees in a circle. And those degrees are denoted by this little circle superscript. And a degree is really not very much. There are 2 lines, this one, and the angle between those is 1 degree. An arc minute is denoted, 2 pi radians is also a full circle. And we'll talk more about that in a little bit.
Radians.
They're radical.
Because they're
radians.
rad.
Yeah, they're really radical. Yeah. So the shorthand notation for the unit of radians is the rad. 60 arc minutes in a degree. So you're going to take this degree and divide it into 60 equal pieces. Here I've done it about 4 or 5 times, but you're going to do that 60 times. And what you end up with is 2 lines that look like that.
That's 1 line.
It's 2 lines.
That's 1 line.
Yeah, it sure darn well looks like 1 line. And the reason is that it's these lines are so close to parallel, you can't tell that it's 2 lines instead of 1. So an arc minute, denoted here by this, it's a little apostrophe, a straight apostrophe. It's called a prime symbol in physics, is very, very small unit. And then 60 arc seconds in an arc minute. So you're going to take this tiny, tiny angle that you can't even see, and you divide that into 60 equal pieces. So an arc second is pretty Small.
Small.
Very
Yeah.
small. Yeah.
The arc length formula relates the arc length S around a circle to the circle radius R for a wedge of angle theta, measured in radians.
Good Greek there, Ren.
Thank you.
Yeah, well done. So the way this works is this formula relates this arc length around the outside here. It's a curved path. It's along the circle to the radius of the circle and the angle here between these two, the two edges of the pie slice that you're dealing with. So, and it's easy to derive this equation, and I'd like to show you where it comes from because it relates to the circumference of the circle. If you apply this to a full circle, well, what is the angle for a full circle? A full circle is 360 degrees. We also talked about a full circle measured in radians being 2 pi radians. Remember that?
Mm-hmm.
And so this is a full circle, 2 pi radians. And then if we plug that into here in this equation, we'll get S is R times that angle, just 2 pi. And if you just use the associative property of multiplication, that's 2 pi R. And that's something that you might recognize.
Okay.
What is it?
That's area of area of a circle?
Circumference.
Circumference?
Yeah, it's called a circumference.
Not a physics teacher.
Yeah. So the circumference of a circle is the distance around the whole circle. So that's just a confirmation that this
Pi r
equation's
squared
valid.
is area.
That's exactly.
You're welcome.
The area is pi r squared. You're very excellent. That's why wonderful. Yeah. So S equals r theta. This turns out to be extremely useful in all over the place in astrophotography. We use it all the time. S equals r theta, and it's mostly useful for when the angle is really small. Those arc minutes, arc seconds, just maybe a degree or two. Very, very helpful formula.
The arc length formula approximates the straight line distance between 2 points to within 1/10 of 1% for angles smaller than 10 degrees.
So here's a 10-degree angle, and and you can see that the circle from which this came is going to be a pretty big circle. And this distance along that arc, it almost looks like a straight line.
It does.
It's just almost straight. And in fact, the distance or the difference between a straight line between these 2 points and the distance along this arc is less than 1/10 of 1%.
So isn't it right that in astronomy that most of the things we're going to be looking at and comparing in the field of view of an astrophotograph are going to be close? They're going to be
1 degree, half a degree,
smaller than 10 degrees.
Maybe distance between 2 stars in photograph might be a minute of arc or a second of arc even and so the nice thing about that is that this distance, the arc length formula, is essentially the actual distance between those two points.
Nice.
If you know the distance to that, the distance r is the distance from here to whatever we're looking at, the Orion Nebula or whatever, then if you can measure that angle and you know the distance to it, then you can figure out how far apart those 2 stars are in the Orion Nebula. Very, very useful.
Yeah. 1 degree is the approximate angular width of your little finger held at arm's length.
Okay, and you see this lovely photograph of me. We're talking about having a finger up. Use your little finger, please. The width of the finger is is about 1 degree. We worked it out, worked out the distance from my eyes to my finger. That's distance is r, and then this width is s, and found out that the angle is about, for me, it's about 1.3 degrees. But it's good enough. Your distance will vary if you have big fat fingers or short arms. But it's roughly a degree. And
Or if you got
really
a lot of salt or sugar that day, you're going to be all puffy.
all puffy, yeah. You've been hiking or whatever. Yeah, so it's a good rough measure, and I use it a lot when I'm trying to understand things.
1 arc minute is the approximate angular width of a human hair, held at reading distance.
So this is Ren's daughter Jocelyn holding a piece of paper to which is taped a hair, and you might be able to barely see it. It's taped to the middle of the paper going roughly vertically. It's a little bit curved. And that hair held at readings, a close reading distance, is about an arc minute in width. So we saw before how the arc minute, those two lines just looked like they were the same. You thought they were the same, but they weren't. It really was two lines. This is another manifestation of really how tiny an arc minute is.
Yeah, it's crazy.
Really, really small.
And just for reference, we pulled one of his nice dark hairs for that one.
Yeah, not one of the gray ones. Yeah.
Nice dark. 1 arc second is the approximate angular width of a human hair, held at the other end of a tractor trailer.
So this is Ren's daughter Olivia in the foreground and Ren's daughter Isabel in the background, holding that very same piece of paper that Jocelyn was holding, with that same hair on the paper. And of course, at that distance, you're just not going to see the hair at all. But
Well, some people with really good eyes might be able to see it.
I don't think so. I don't think it's physically possible. Although we did an experiment once with the family, and there were people that got pretty close to being able to see that. So it's an extremely small measure. An arc second is, just imagine a whole tractor and the trailer, the long trailer, and then putting a hair at the end of that. That's what the size of an arc second is. And like we mentioned in the introduction, our equipment, and probably yours also, will guide to within sometimes an arc second or half an arc second. It's just incredible to me that you can actually keep that telescope pointed to within the width of a hair at the other end of a tractor trailer. It just says a lot about the technology for today.
Yeah. Extrasolar stars are much too distant to resolve as disks using most amateur telescopes.
So this is Olivia in the foreground, and Isabel and her little sister Eleanor in the far distance, about 360 meters away.
All mine, and they were so happy to help.
Yeah, they were. No, they were happy. They were good.
They were sort of happy.
So 360 meters away. So 100 meters roughly is a football field. So this is 3 or 4 football fields in distance. They're holding up that same piece of paper. You can see right here that Isabel's holding with that same hair. And those extrasolar stars, the very biggest star in our sky, the one with the biggest disk in our sky, is R Doradus. And its size is this size. It's the width of a human hair at 360 meters. There's no way you're going to be able to resolve that with your amateur telescope, sorry to say.
Wow.
We'll say more about sizes of stars in images which are not this small. They're big blobs depending on the magnitude of the star. We'll say more about that in a later video. Thanks for watching.
And we'll see you next time.